Hi everyone, we are Team Felix, and this is our submission for Quant-A-Thon 2026 Battery Behavior and Chemistry Modeling powered by Quantum Optimization. Here's the problem we're solving. Batteries degrade, but how they degrade depends on temperature, usage, and charge cycles. If we can accurately predict a battery's state of charge, state of health, capacity fade, and thermal response, we can prevent failures, extend battery life, and make charging smarter. That's exactly what our system does, using AI models and quantum optimization to make those models sharper. Our approach starts with real battery cycling data, voltage, current, temperature, capacity. We feed that into two models, an LSTM for time series forecasting and XGBoost for health prediction. The twist is QuantumNow, our quantum inspired optimizer, which handles feature selection and hyperparameter tuning. The end result, accurate predictions for SOC, SOH, capacity fade, and remaining useful life, all deployable into a real battery management system. This is our full pipeline, end to end. Data comes in from battery datasets and sensors, gets cleaned and preprocessed, and critical features get extracted. That's where QuantumNow steps in, optimizing which features matter and how our models should be tuned. Those optimized configs feed into our LSTM and XGBoost models, which output predictions that plug straight into real-world applications. BMS dashboards, optimized charging, and predictive maintenance alerts. Let's zoom into that quantum layer. It's simple. 3 steps. High-dimensional battery signals go in. Our QIEO solver processes them using a QUBO formulation, and an optimized model configuration comes out. Why does this matter? Because battery datasets are huge and high-dimensional. Testing every feature combination classically is expensive. Quantum-inspired search explores that space intelligently. Better accuracy, fewer redundant features. So how does that stack up against classical tuning? We're benchmarking head-to-head QuantumNow versus grid search, random search, and Optuna. Our target, a smaller, more targeted feature set, lower training time thanks to guided search instead of brute force, and prediction accuracy that matches or beats the classical baseline. This comparison is the heart of what makes our submission credible, not just conceptual. Under the hood, we're using a fully open production realistic stack. PyTorch and XGBoost for modeling, Scikit-learn and Pandas for the classical pipeline, and QuantumNow through the BQPhy SDK for optimization. What makes it innovative isn't just using quantum-inspired search, it's that our pipeline predicts both short-term and long-term battery behavior and directly benchmarks quantum against classical with real numbers. Finally, is this actually buildable? Yes. We're using public datasets like NASA's battery aging dataset, so there's zero data collection bottleneck, and even if quantum hardware access is limited, our pipeline gracefully falls back to a simulated annealing solver. Our roadmap is clear: data prep, baseline models, QuantumNow integration, benchmarking, and finally a full dashboard with a stretch goal, a smart charging recommender. And to be transparent, QuantumNow is quantum inspired, not real quantum hardware, but it's accessible today, with a real path to quantum as it scales. Thank you. That's Team Felix's take on quantum optimized battery modeling.